All right, welcome to the Explainer. Today, we're cracking open the mathematical toolkit that honestly powers a ton of our digital world. We're talking about the discrete Fourier transform, and specifically the core rules, its properties that make it so powerful. So, let's kick things off with a question. Ever wonder how your computer sees the frequencies in a signal? You know, like in a song or an image. How does it actually tell the bass from the treble? Well, it uses this incredible mathematical prism for signals. It's called the discrete Fourier transform, or DFT for short. And that prism analogy, it's perfect. Just like a real prism takes white light and splits it into all the colors of the rainbow, the DFT takes a complex signal and breaks it down into all the simple frequencies it's made of. But here's the thing. For this prism to be actually useful, it needs a consistent set of rules, right? It can't just work randomly. These rules are its properties. And that's exactly what we're going to dig into today. All right, let's do it.
Okay, first up, let's talk about the DFT's ground rules. These are the two most basic principles that really set the stage for how it behaves.
The first one is called linearity, and it's pretty much what it sounds like. It just means that if you scale a signal or add a couple of signals together in the time domain, well, their DFTs scale or add up in the exact same way in the frequency domain. Super predictable. And you can see the math right here. This formula, it's just a fancy way of saying what we just talked about. You mix two signals, their frequency spectra just mix together in the same way. Simple as that. No weird side effects. All right, ground rule number 2 is periodicity. Now this one's cool. It basically tells us that the DFT's output, its frequency spectrum, isn't infinite. It's periodic. It just repeats itself over and over again. The proof for this is actually pretty neat. It shows that the frequency info you get at point K is exactly the same as the info you get at K plus N, where N is the length of your signal. And why does this happen? Well, it's because a little chunk of the formula always works out to be 1. It kind of cancels out, which is what forces the pattern to repeat. And this image here is a perfect way to visualize it. Just like this signal repeats in a predictable cycle, the DFT's frequency spectrum does the exact same thing. It just loops. Okay, so we've got our ground rules down, linearity and periodicity. Now, let's move on and see what happens when we start messing with the signal a bit. What happens if we shift it? This is where things get interesting. It's not just a simple shift where things fall off the end. It's called a circular shift. Think of it like your signal is on a circular track. When you push the values along, anything that falls off one end just wraps right around to the beginning. Nothing gets lost. Check this out. On the left, you've got the original signal, and on the right, that's what it looks like after a circular shift of 2 spots. See how the last 2 values didn't just vanish? Nope, they wrapped right around to the front of the line. This table here breaks down the math behind it. It uses something called modulo arithmetic to figure out the new positions. So to find the new value at position 0, you take the original position, 0, minus the shift, which is 2, and that gives you -2. But since it's a 4-point signal, we do a modulo 4, which basically means we wrap around. So the new value at position 0 is actually the old value from position 2. It's a perfect mathematical wraparound. Okay, next up is a property that is an absolute game changer. It's a shortcut that saves a massive amount of computing power and makes the DFT actually practical for things like your phone or computer. So let me ask you this. For a real-world signal, we're talking audio, images, things that don't have imaginary numbers, do we really need to compute every single frequency component? Is all that work necessary? The answer is a big, fat no, and it's all thanks to this awesome property called conjugate symmetry.